Okay, today I want to talk about buffer solutions, or you can call it buffer solutions, and sometimes it's called buffered solutions. But I want to introduce what they are, what they do, and introduce the one of the equations on your formula sheet called the Henderson-Hasselbalch equation, and when to use it. But this lesson we won't be talking about buffer attack questions. We'll do that in another lesson. But we just want to know what a buffer solution is, how to recognize you have a buffer solution, how they work, and then how to calculate the pH of a buffer solution, or even how to estimate what the pH of a buffer solution will be. All right. So let's go to it. All right. So the definition of a buffered solution or a buffer solution is an aqueous solution which resists pH change when a strong acid or base is added. Right? So we have a solution, a water-based solution, and we add strong acid to it or we add strong base to it. So essentially when I say add strong acid, it could be any of our 7 strong acids that we memorize. And when we say strong base, maybe we mean like a hydroxide salt. So an example of a strong acid, HCl, an example of a strong base, sodium hydroxide. And in this scenario, we really don't care about the spectator ion. So if I'm adding HCl, I don't care about the chloride. I just care that I'm adding H+. And if I add sodium hydroxide, I don't care about the sodium. I just care that I'm adding hydroxide. So it's a solution where a buffer solution is a solution where you have certain things dissolved in your solution that will help resist pH change. Meaning, if I add H+ to my solution, my solution's pH should decrease by a lot. And if I add OH- to the solution, my solution's pH should increase by a lot. But a buffered solution somehow, and that's what we're going to talk about today, resists the change in pH. So if I add H+, the buffer solution can kind of take the H+ out and replace it with something else. Okay. So again, it's a solution that resists pH change. So I have this solution, I add strong acid to it. I'm expecting that if I add strong acid to a water-based solution, that the pH is going to drop dramatically. But I check the pH again, and somehow the pH only changed a little bit. Okay, so if you just add add strong acid to water, the pH is going to dramatically lower. Even just a little bit of H+ added to water drops the pH big time, right? And the same thing's true. Adding a little bit of strong base, adding a little bit of hydroxide should increase the pH of a water-based solution pretty quickly. Add a little bit of OH, the pH is going to skyrocket. And so what a buffer solution is a solution that when I add that H+ to the solution or I add that OH- solution, the pH doesn't change much at all. Okay? So a buffered solution is a solution whose pH does not change much when a strong acid or base is introduced to the solution or the system. All right? That's what a buffered solution is. All right? So how do you know a solution is a buffer solution or a buffered solution? Well, this is what you have to have. You have to have a weak acid and its conjugate base in solution at the same time. Or you could flip that. You could say a weak base and its conjugate acid. Okay? If a solution has both conjugate weak pairs, if it has both of the conjugate pairs, and they're weak acid and its conjugate weak base, or weak base and its conjugate weak acid, if both of those things are in solution at the same time, your solution is a buffer solution, which means it can resist pH change if now you add H+ strong acid to it or OH- strong base to it. Okay? So if you have a weak acid and its conjugate base or a weak base and its conjugate acid in solution at the same time, you have a buffer solution. Okay? So if we want to break that down into our generic weak acid and its generic conjugate weak base, if you have HA, which is a weak acid in solution, and you have A- in the solution at the same time that you have HA, if both of those things are in your solution, you have a buffer. All right? So let's think. What if I took an HF solution, so a hydrofluoric acid solution, and I added some sodium fluoride? Well, what we need to recognize, if I add sodium fluoride to the solution, what I'm really adding is sodium ions and fluoride ions. So in the solution, I have HF already because it's an HF solution, and I added fluoride ions. I don't care about the sodium. But what we have to recognize is if I make the solution this way, if I take a hydrofluoric acid solution and then I take some sodium fluoride salt and throw it in there, and the sodium fluoride dissolves, I know I'm adding fluoride ions. Well, notice I have both of these two things in solution at the same time, HF and F minus. That means I have a buffer solution because I recognize that this is a weak acid and this is its conjugate base, and I have a source of the conjugate base and I have a source of the weak acid. I have them in solution at the same time. I have a buffer system, all right? You could make an ammonia solution and then add some ammonium chloride. And what you would recognize is, okay, I have ammonia in solution and then I added some ammonium. Well, if you know ammonia is a weak base and ammonium is its conjugate acid, now you have both of these in solution at the same time. You have a buffer system, all right? All right. So how does a buffer system work? So how does it resist pH change? Okay, so the first thing we have to understand is strong acid will react with any base, whether it's a strong base or a weak base. So if you add H plus will react with any base, okay? Or the opposite is true. If you add strong base, so if you add OH minus to your solution, it will react with any acid to completion. So OH minus will take out any HCl, it would take out any HF. It doesn't matter if the acid's strong or weak. If you add OH minus to your solution, the base is going to react with any acid, whether it's strong or weak, to completion, okay? So let's imagine this is our buffer system. So if you know you have a buffer system, two things you kind of have to do. You have to recognize what is the base of the buffer system and what is the acid of the buffer system. So if this is my buffer system, I got ammonium ions and ammonia. I got to know that of these two conjugate pairs, NH3 is the base and NH4 plus is the acid. That's the weak acid of my buffer system, and that's the weak base of my buffer system, okay? So now let's understand what we do. So I have my solution. I recognize it's a buffer because I have both of these in solution at the same time, and I add some HCl to it. That's strong acid. Well, we know that this is a buffer, so what does that mean? It means the pH isn't going to drop dramatically. Somehow, the solution is going to mitigate the amount of H plus added, all right? And so again, I add HCl, I got to recognize that's a strong acid, and so really all I care about is H plus. You're adding H plus and Cl minus. Remember, Cl minus is neutral in solution, so the only thing that can affect pH of this solution right now, from where it is right now, is adding H plus to it, or OH minus, in this case H plus. So H plus will react with any base. So remember, what is the base of the buffer? The base of the buffer is the ammonia in this case. So if I add strong acid, the strong acid will always react with the base component of the buffer system. So I got to be able to look at this buffer system, recognize that this is the base and this is the acid. If I were to add strong acid to it, meaning if I added H plus to the buffer, it's going to react with the base part, okay? So what happens is the buffer system takes out any H plus I add. How? The weak base of the buffer system will react with the H plus of the buffer system and produce more of the acid component. And remember, this is a strong acid and this is any base, this reaction goes to completion. So as long as I have NH3 in my solution, which is the base component of my buffer system in this scenario, any H plus I add will be taken out, right? The NH3 is going to sacrifice itself and take out the H plus and produce more of the ammonium. So as long as you have the NH3, it'll take out any H plus you add. And a way to think about it is, how does the buffer system work? So if I add strong acid, the pH is going to decrease, but a buffer system is going to mitigate how much the pH is going to lower. And so really what's happening is the buffer system is converting strong acid into weak acid. So the pH is going to go down, but just a little bit. If all I was adding was H plus and the H plus stayed in solution as H plus, the pH would drop dramatically. But because the H plus is being taken out by the base of the buffer, the pH is going to go down, but just a little bit. Because again, I'm replacing strong acid H plus with weak acid ammonium in this case. Okay. So what does a buffer do? How does it survive a strong acid attack? It takes that strong acid and converts it into weak acid. So the base component of your buffer will take out the H+, but notice in doing so, you're going to lose this component of your buffer, but you're going to gain this component of your buffer. Okay. All right, well, how does the OH minus work? Okay, well, what if I add strong base? So let's say I added magnesium hydroxide. Again, we don't care about metal ions in solution. We just care that I'm adding hydroxides. Hydroxides are strong base, all right? So again, if this is our buffer system, remember, this is the base of our buffer, the ammonia, and the ammonium is the acid component of our buffer. If I add hydroxide to that, the hydroxide, the strong base, is going to react with the acid component, or the strong base is going to take out the acid component of my buffer. Okay, so any added OH minus will react with the acid component. In this case, that's the NH4 plus. And what will happen is the OH minus will take an H plus away. You'll get ammonia and water. Okay, so notice any hydroxide added will react with ammonium and produce more ammonia. So you're going to be losing the ammonium, but you're going to be gaining the ammonia. And so think about it this way. If you add strong base to your buffer system, the buffer is going to take out the strong base you added, OH minus in this case, and replace it with weak base, ammonia in this case. It's going to buff it out, okay? So as long as you have ammonium ions in that buffer solution, they'll take out any hydroxide that you add. And this reaction will just go to completion until you run out of ammonium, okay? Okay, so again, how does a buffer system work? How does it resist pH change when adding a strong acid or a strong base? If you add a strong acid, it resists pH change because the base component takes out the strong acid you added. If you add a strong base to it, the acid component of your buffer takes out the strong base that you added. Okay, it's converting the strong base into weak base. We're converting the strong base hydroxide into weak base ammonium in this case. Okay. All right. So a generic buffer system would be HA and A minus. We'd have to understand that this would be the acid component and that's the base component. So if this is my generic buffer system, if that's what I have in solution, and I add H plus, I know H plus will react with the base component of the buffer, A minus, and produce more HA. But if I add strong base to that same buffer system, the OH minus is going to react with the HA of the buffer, the weak acid of the buffer component of the buffer system, and produce more A minus. Okay, so this is how a buffer system protects from strong acid, and this is how a buffer system protects from the addition of strong base. Okay. And a thing to note for future problems when we get to more complicated buffer problems is to notice that as a buffer system works, as a buffer system takes out the hydroxide that you add, or as it works and takes out any H plus that you add, you lose one component and you gain the other. So as I add OH minus, I'm losing HA, I'm losing the acid component, but I'm gaining the base component of my buffer. As I add H plus, I'm losing the base component, A minus, and I'm gaining HA, the acid component. Okay. So a couple things we want to talk about is how do we select a buffer system, right? Because we could have any weak acid and conjugate base or any weak base and its conjugate acid. So how do we know which buffer system that we want? And basically, it just depends on what pH. What pH do you want to be close to? Like, do you want your buffer system to be close to a pH of 7? Do you want your buffer system to be close to maintain a pH of 10? Do you want your buffer system to maintain a pH of 4? Right? It really depends on what your target pH range is for your solution. Okay? And so here's how you do it. The buffer system will keep the pH of a solution close to what we call the pKa of the acid of your buffer. Okay? And so remember, pKa is just the negative log of the Ka. Okay? So let's use acetic acid and acetate as our buffer system. So acetic acid is the acid component of our buffer, and so it has a Ka value. And acetate is the base component of our buffer in this example, and so it has a Kb value. Okay? Well, if you know the Ka of the acid component, so the Ka of acetic acid is 1.8 times 10 to the negative 5, If you take the negative log of that, which is the pKa, that'll tell you the pH that this buffer system will stay close to. So the negative log of 1.8 times 10 to the negative 5 is 4.74. So if I have an acetic acid acetate buffer system, I'm going to be close to a pH of 4.74. Okay? So let's say I wanted to make a solution that maintain a pH around 5, then I might use this buffer solution because I know the pH is going to be close to 4.74. And you could actually figure out exactly what concentrations of each component you need to dial up a certain pH. Okay, we know it's going to be close to this pH, okay, because that's the pKa of the acid component of the buffer, but you could adjust what pH is actually equal to by adjusting the concentrations of each of these, all right? All right, let's use another example. What about the ammonia-ammonium system? All right, well, here's kind of crazy. Remember, the pH is going to be close to the pKa of the acid component of the buffer. So let's say I had this buffer system and I wanted to know which pH my buffer system is going to be close to, okay? Well, again, you'd have to look at the two and know that this is the base component of your buffer and this is the acid component. And what if they gave you the Kb of ammonia? Okay, so they gave me the Kb of ammonia, but I know a buffer system is going to be close to the pKa. Well, they didn't give me the Ka, they gave me the Kb. Well, remember our Kb and Ka relationship when we have conjugates. So they gave me the Kb of ammonia, but it's just a quick calculation to get the Ka of ammonium. So that's the acid, ammonium is the acid component of my buffer system. So if I figure out the Ka for ammonium, and take the negative log of it, that's going to be the pH that this buffer system stays close to. And so the negative log of this is 9.25. So if I needed a base solution, if I needed my pH to be basic of my solution and I needed a buffer system, then I might use this because I know the pH of this buffer system is going to be close to 9.25, which is the pKa of the ammonium of the buffer system. Okay. Now, the other way you could go about it is you could say the buffer system is going to maintain a pOH close to the pKb. I mean, it's the same thing, but we're usually focused on pH, okay? But if you knew the pKb, if you knew the Kb of the base component of your buffer, and you took the negative log of that, which would be the pKb, that's what the pOH is going to be closest to. So if you subtract that from 14, that's what the pH would be close to, all right? All right, so another thing we need to know is how to calculate the pH of a buffer system. So it's really important to recognize when we do have a buffer system because we have an equation. If we have a buffer system and I want you to calculate the pH, hey, there's an equation for that. And it's on your formula sheet. It's this one right here. This is what's on your formula sheet. It says pH equals pKa. So remember, pKa is just the negative log of the Ka. And that would be the Ka of your acid component, okay, plus the logarithm of this ratio, the concentration of the base component over the concentration of the acid component of your buffer. All right, so if we did a generic buffer solution, it would be pH equals pKa, and that would be the negative log of the Ka of this acid, whatever HA is, plus the log of the concentration of A minus over the concentration of HA. It's always base over acid when it's pH. This equation is called the Henderson-Hasselbalch equation. So when you have a buffer system, boom, reach for the Henderson-Hasselbalch if you have to calculate the pH. So you got to be able to, A, recognize you have a buffer and know that there's an equation for it, okay? Now, we could make this Henderson-Hasselbalch, we could adjust this equation to make it equal to pOH. And the way that would work is you could say the pOH equals pKb, so the negative log of the Kb of the base component of your buffer. And we would flip the ratio. It would be acid over base component of your buffer, okay? Now again, this is not on your formula sheet, okay? But this one is. So you probably just want to focus on this one. And remember, if you're given the Kb, you can figure out the Ka real easily, all right? But it's always, if you're using the pH one, it's always the base component over the acid. So let's say we were doing the ammonia-ammonium buffer system. It would be the negative log of the Ka of ammonium, right? That's what we would plug in here. And we would put ammonia's concentration on top and NH4 plus's concentration on the bottom, okay? All right, so let's say we were using this buffer system, hydrofluoric acid and the fluoride ion. So what we'd have to recognize is that HF is the acid component and F minus is the base component. So it would be pH equals pKa, and that would be the negative log of the Ka of HF. So I would have to either look that up or it would be given to me. And it would be plus the log, and again, it's always base component over acid component. So in this case, it would be F minus over HF. And those are molarities, okay? So let's do a sample problem. Let's say we make a buffer system by taking 8.2 grams of sodium acetate and we dissolve it in a solution of acetic acid. And they give us the Ka of acetic acid, and they give us the volume, and they tell us the molarity of acetic acid. And we want to find the pH of the solution, okay? So they say assume that, so we took this solid salt and we added it to 1 liter of the solution, but they said assume the volume is still 1 liter, all right? So all we have to do is figure out the molarity of acetate from this 8.2 grams of sodium acetate that we add. All we have to do is figure out the molarity of acetate. We have the molarity of acetic acid, and so now we just plug into the Henderson-Hasselbalch, all right? So first we recognize we have a buffer. We have the acetic acid and the acetate. We take the negative log of the Ka, which was 4.74, and we would say plus the log, and it would be the acetate concentration over the acetic acid concentration. Well, they gave us that, 0.15. And so all we have to do is figure out the molarity of the acetate, and that would be easy. 8.2 divided by the molar mass of this compound. So if we calculate the molar mass of this, it comes out to be 82. So 8.2 divided by 82 is 0.1. And so we have 0.1 moles of acetate in 1 liter. So the molarity of acetate is 0.1. So we would plug in the molarity of acetate, 0.1, plug in the molarity of acetic acid, 0.15, and we just do 4.7 plus the log of that ratio, and we get 4.56. Okay. Now, what I want you to know is that when these concentrations are equal, you would get the log of 1, and the log of 1 is 0, and that's when pH equals pKa. So when you have equal concentrations of your buffer components, remember this is the base component and that's the acid component. When you have equal concentrations of those, the pH equals the pKa of the buffer, of the acid of the buffer component. Okay, so if we had 0.15 divided by 0.15, we'd get pH equals 4.74. Now, another thing I want you to recognize is notice that the pH of the solution we just made up here is slightly more acidic, has a lower pH than the pKa. And if you think about it, look at the buffer system. We have more of the acid component of our buffer system than we do the base component, so it should make sense that the pH is a little bit lower than the pKa because we have more acid than base. But if it were flipped, if we had more base than acid, then this pH would end up being higher than the pKa, all right? So if you're using the Henderson-Hasselbalch equation, when you have equal amounts of A minus and HA of your buffer components, the pH is going to be the negative log of the Ka always, okay? If you have more acid than base, the pH is going to be less than the pKa. And if you have more base than acid of your buffer components, so more A minus than HA, your pH will be a little bit more basic, so above the pKa, okay? All right, so that's just kind of a quick intro to buffer solutions, how they work, okay, the Henderson-Hasselbalch equation. We're gonna do a lot more practice with it. We're gonna do some buffer attack questions, meaning that the sample question we just did there at the end was, hey, here is a buffer solution, what's the pH? So just plugging in our information into the Henderson-Hasselbalch equation. But eventually what we're gonna have is we're gonna have a buffer system that's at this certain pH, then we're gonna attack it with strong acid or strong base, and we want to figure out the pH after the attack, okay? So we'll do some practice problems with that in our next video lesson, but I just wanted to kind of introduce what buffer systems are, how they work, and eventually we'll add on to that, all right?